So everyone, thank you for attending the annual Concrete Solutions Award Ceremony and Virtual Student Awards today. Thank you to everyone who came and attended the interviews. Thank you to all of our teams. On behalf of the ACI President Scott Anderson, we would like to welcome you to the 2026 Virtual ACI Student Awards Ceremony. Today's program is sponsored by the Student and Young Member and Faculty Activities Committee and S801 Student Competitions Committee. SciFac is led by Alyssa Naro, who will have some words for us later today. The Students Competitions Committee is led by our chair, Andres Matos, and our secretary, Maddie Murphy. Thank you so much for the amazing event that they put on. We could not do all that we do without them. They truly make these events what they are. The Graduate Student Convention Travel Stipend Program is open to students now pursuing a master's or doctoral degree. Applications are accepted on a one-time per year between April 1st and June 15th. Grad students receive up to $1,000 to cover travel expenses related to attending the ACI convention. The undergraduate the undergraduate research session, we are inviting students to submit abstracts on concrete materials, structural design, construction, or other concrete related research for the upcoming virtual undergraduate research session. Those abstracts will be due June 14th. The session will be held online via Zoom on August 6th. You can learn more by visiting the ACI website at concrete.org under the News and Events page. The ACI Foundation provides undergraduate and graduate students with opportunities to receive fellowships in the amount of $10,000 for USD for students enrolled in a university in the USA or Canada. All students, including international students, can apply to receive a $5,000 scholarship. The application period will open on July 1st and close on November 1st. Learn more at www.acifoundation.org/scholarships. Be sure if you're one of our students who are looking for other opportunities to attend convention and things and to be involved, this is one of those opportunities that I would definitely check out. The ACI Student Leadership Council is our only student-led committee. We wanted to introduce our committee today. I'm not sure how many of them we have here today with us, but we have a new board. The mission of the Student Leadership Council is to provide students with tools to successfully run an ACI student chapter, develop presentation and public speaking skills, and prepare students for leadership roles within ACI committees. This committee meets on Monday afternoon during the ACI Concrete Convention. Students interested in joining S805 should submit their application online at www.concrete.org/get-involved/committees. The student chapter leaders interested in presenting at the upcoming fall convention should contact students@concretes.org if you are part of a chapter and interested in presenting at one of the student-led events. This is a great way to get involved as an undergraduate if you're looking for other opportunities as well. Our new chairs are Adam Johnson, Carolina Treboni, and Mahdi Mirabashami. Feel free to introduce yourselves to them if you're ever at convention. They're all wonderful people. Now we are going to get straight into announcing our winners for the Concrete Solutions competition. In third place, we have for most innovative design. Third place, the Hashmite University ACI student chapter. Congratulations on you all. I'm gonna see their video here too.
always took this sound for granted. Who could have ever predicted that one day we would lose access to these machines and desperately miss the very labs that build our world? Of course, you remember this nightmare of the COVID-19 when no student are allowed to be in their university. We thought that was a once-in-a-lifetime disruption. We were wrong. The closure of our physical campuses has become a tragic, escalating pattern. In 2021, the Tigray War brought education to a violent halt. Institutions like Mekelle University faced direct airstrikes, extensive looting, and a devastating loss of life. In 2022, the war in Ukraine saw historic engineering halls reduced to rubble, forcing students to trade classrooms for bomb shelters. By 2023, the conflict in Gaza led to the near-total collapse of higher education infrastructure and struck the Islamic University of Gaza multiple times, reducing its main campus and laboratories to ruins. The destruction spread further in 2024 as severe airstrikes across Lebanon forced the complete suspension of education, shutting down universities across Beirut and leaving the future of an entire generation in limbo. And the threat isn't just human conflict. In 2025, nature joined the assault. Catastrophic wildfires swept through Los Angeles, choking campuses in thick smoke and turning universities into sudden evacuation zones. Now, in 2026, severe geopolitical conflicts, including unprecedented Iranian-American tensions, have triggered massive protests, security barricades, and historic campus lockdowns worldwide. Year after year, the lesson is clear. The physical laboratory is fragile. When the world shuts down, where does learning go?
Pandemics, wars, conflicts, and fires all have kept the students away from the universities and labs, making education more challenging, and we were no exception. As civil engineering students at the Hashimite University, we asked ourselves, when the doors close, how can the students understand the behavior of concrete in a way that can simulate the lab experience? We sat down, thought, and built a solution, a virtual concrete lab. It aims to allow students to experience being in the lab without actually being there, and to perform all the experiments needed on concrete, so the education can continue even through the hardest of times.
Going through our vision, we currently never will see it as a competition. We only see it as our mission. Let's get a small tour in our virtual lab. University concrete laboratories closed for many reasons: a corona pandemic, war, or any crisis that suspend campus operations. If that happens, students lose the ability to touch, test, and understand the material they will build with. This virtual lab restored that completely, instantly, and at zero recurring cost. Now let's use our daylight to do some concrete mix design. This operation, according to ACI 211.1, let's target at 25 megapascal, medium slump, and 90 millimeter maximum aggregate size. Approximately, we have 2 kilograms of water, 4 of cement, 7 of sands, and 11 of aggregate. Now, let's add the material to the mix, starting with water, 2 kilograms, 4 for cement, 7 for sand, and 11 for coarse aggregate. Now, after done with that, let's mix them. Put them in the mixer and run the mix. After that, let's dump to the trolley. Now we have to cast. Firstly, let's cast one cylinder, then one cube. Our sample, by default, are located in the water tank. We use the water tank to cure and age them. For example, for the cylinder sample, I'll age it for 7 days, and for the cube, I'll do it for 28 days. Now let's use UTM to crush our samples. Firstly, let's do a compression test on our cylinder. Please get your eyes on the cylinder so you can see the cracks. Also, for the monitor to see the curve, and at the end, you see the failure type. After that is done, let's do the same for the cube. Please get your eyes on the cube, see the cracks and the failure. Finally, let's do tensile test for our steel sample. Please focus on the load strain curve. After the failure, now let's open our notebook. Every student must have one. Firstly, leave notes about the mix design we did. Then, we wrote down the tensile test result. Now, let's show our calculations. Now, let's do something to make the memorization more easy. Let's put our sketch about the failure shape and the curve about the stress strain. After steel, we have the concrete cube. Do the same thing, we've got some results, and now we need to show our results and sketch some things. The last thing to do in our day is a slump test. Firstly, let's fill the first third of the cone by our mix, then roden it. Now, let's do the same thing but for the second third. Finally, the third third. And now, let's lift the cone. Then, measure it. Finally, let's see the result on our monitor. And with that test, our concrete day is coming to the end.
What we're building today is a start, a prototype for something much bigger. A full virtual concrete lab powered by AI, so students anywhere can have hands-on experience on the material without ever needing to get to a lab. Real experience, zero barriers. Instead of months and thousands of dollars, minutes, minimal resources. Because concrete is the foundation, and no matter who locks the door, the students deserve to feel it in their hands.
Perfect. And thank you so much, Ashmont University, for you guys' amazing video. And now for our second place winner. Drum roll. Oh, imaginary drum. Perfect. Universidad Tecnológica del Peru. Congratulations to you all on second place. Innovation category.
Every year, the world produces more than 1 trillion bricks. They are a silent part of our homes and of what we understand as progress. They are there, and we don't notice them, because in the midst of comfort no one asks how much that is one cost the planet. They come from fertile soils that do not regenerate, and each ton emits more than 200 kilograms of carbon dioxide, consuming 706 kilowatt hours, enough energy to power an average home for 10 weeks. In addition, just the walls of a single house require more than 4,000 bricks, which mean emitting between 2 and 4 tons of CO2 into the atmosphere. On a global scale, this is still being construction. As Antoine Lavoisier once said, nothing is created, nothing is lost, everything is transformed. However, in this sector, we are still losing too much. If we have advanced so much, why are we still manufacturing them the same way as more than 1,000 years ago? Even knowing that their waste does not disappear, it can be broken, crushed, turned into powder, but it will remain. But what if that waste were not the end, but the beginning of a new material? From these residues, it is indeed possible to form a new material. Recycled brick powder, rich in silica and alumina, can like alkaline activation and reorganize into a stable network with cementitious properties. This is known as geopolymer materials.
Unlike conventional brick, this process doesn't require curing at high temperatures. Studies have shown that geopolymers can develop at a room temperature or under moderate curing conditions, with values close to 60 degrees Celsius. In addition, they reach compressive strength of up to 32 megapascals, with lower absorption rates and reduction in drying shrinkage of up to 35%, which improves the dimensional stability of the materials, complying with TMS 402 regulation and other international standards in America and Europe. However, not everything is so simple. As thermal comfort decreases as the matrix densifies and reduces the permeability of its pores. Additionally, the grading process and the mixture with conventional activators necessary to achieve geopolymerization increase cost. Here is where waste change the focus again. Science it's not in a single place. It comes from different sources with diverse composition and characteristics. However, it's precisely that diversity that opens up a new possibilities. Today, waste such as the plastic, oils, and other byproducts are already being reused in agriculture or energy production, reducing cost and pollution. For us, this poses direct challenge in the way we build. The goal is to design a brick capable of meeting standards such as ASTM C90 and ASTM 62, using waste in a way that even emits 80% less carbon dioxide than common method. An idea that is beginning to take shape as a real impact on the decarbonization of the construction sector. But is it possible to manufacture bricks with what is commonly known as a garbage?
The response appears again in the same place, and a second curiosity materializes this possibility. Rice husk ash, an agro-industrial residue derived from a global rye production that exceeds 776 million tons annually. This high production volume generates large amounts of waste, whose valorization represents a sustainable opportunity in the construction industry. By incorporating 5% of this ash into the brick powder mixture, the high content of amorphous silicon manages to modify the thermal response of the material, making it comfortable and functional. At the same time, it also achieves an increase in initial strength surpassing 40 MPa. But it's not all about the fines, as the activators, which allow the reaction to occur and transform the combination of rice husk ash and brick powder particles into a structural material, are essential for the system to truly function as a whole. Without them, there is no matrix, there is no cohesion, and therefore there is no brick. Conventional activators, such as sodium hydroxide or silicates, concentrate a large part of the cost and environmental impact. As long as there's no continuous sustainability will end up breaking down. For this reason, it is proposed to use alkaline solution recovered from industrial effluents from sectors such as textiles, chemicals, or treatment plants as a viable alternative. These wastes usually contain alkaline compounds capable of activating the dissolution of aluminum silicates, allowing the induction of eupolymerization in a manner similar to commercial activators. The reuse not only reduces the need for high-cost chemical inputs, but also decreases the environmental impact associated with their production and final disposal. Integrating into the circular economy approach we propose, thus, when a system stops relying on what generates the problem, it begins to sustain itself on its own coherence. Under this logic, bricks cease to be a conventional material to become a sustainable alternative capable of meeting the demand of world constant growth, urbanization, and industrialization.
A material where waste stops being a problem and becomes the starting point to design, innovate, and build in a more efficient and sustainable way. As an old proverb warns, only when the last tree has been cut down, the last river poisoned, and the last fish caught, we will realize that we cannot eat money. We are still in time to avoid it, and also to build better, with less and for more. We are not just proposing a new brick, we are proposing a new way of building. One that takes what we discard today and turns it into opportunity, where each brick stops being just a construction element and tells a story of innovation and sustainability. The technology is ready. The question is, are we?
Absolutely great video. Congratulations, team, on second place. And now for the winner of the innovative design category, we have University of the Philippines, Los Baños. Congratulations, team.
Concrete is the most widely used construction material for roads, dams, and towering structures that pierce the sky. Its development has continued since its discovery, driven by the persistent challenges associated with it. These emerging solutions are expected to aid the younger generations. Hi Joanna, how old are you?
I'm 8.
Oh, you're 8. Well, in your age, have you seen tall buildings?
Like malls and schools? They're so cool.
Right, well, even your home, they are made up of this, and it contains sand and large stones and even small ones. Can you see it from here?
Yes, but how do they stick together?
Well, cement binds them together. However, there is a problem with cement. Cement manufacturing contributes about 7 to 8% of the world's total annual carbon emissions. The production of cement involves the crushing and grinding of raw materials, followed by proportioning and high temperature burning. Firing these materials requires temperatures ranging from 1350 to 1550 degrees Celsius. This energy-intensive process is one of the reasons why the cement industry has a high contribution to carbon dioxide emissions, producing approximately 1.5 billion metric tons of carbon dioxide in 2024.
If that's the case, how can we produce concrete without the use of cement? Is that even possible? From what I've learned from our science class, cement is one of the key components in making concrete.
Yes, it is possible. We have geopolymer concrete that doesn't use cement.
Oh, that's good. We can now eliminate the use of cement.
That's right. However, geopolymer concrete does not use cement as its binder. Instead, it uses aluminosilicate materials such as fly ash, a waste product from electric power generating plants. It undergoes a process called geopolymerization. It starts with the dissolution of fly ash, where silica and alumina are released into the mixture. These species then start to reorganize and form a three-dimensional structure of silicon-oxygen-aluminum bonds. The 3D network becomes denser and stronger, leading to the strength development of the concrete. However, geopolymer concrete is inherently brittle due to its highly cross-linked network. As a result, geopolymer concrete becomes prone to cracking. As a graduate from the university, do you have any idea how we can address this problem with geopolymer concrete, specifically with cracking?
From my undergraduate thesis, yes. This can be addressed using the microbial-induced calcium carbonate precipitation, or the MIC. And it goes this way. So when the self-healing concrete cracks, the water will seep through the cracks, activating the dormant bacterial spores. Once activated, it will metabolize the available substrate and nutrients in the concrete matrix. As a result, the bacteria induces calcium carbonate precipitation as its byproduct, hence sealing the crack.
But don't you think the concrete matrix is pretty harsh for bacterial spores to thrive? How are we going to incorporate the bacteria into the self-healing geopolymer concrete?
There's been many ways to immobilize bacteria in existing self-healing concrete research. So we take advantage of the components that's already in the concrete, such as aggregates, as carriers of bacteria, as well as the nutrients.
That's so interesting. Can you please tell me more?
We're looking into recycled concrete aggregates, or the RCA, as carrier for bacteria. The porous nature of RCA serves as protective, cost-effective vessel for microbes that repair cracks through calcite precipitation. The incorporation of bacteria in RCA also serves as its treatment through the very same mechanism used for self-healing, which is the MICP, thus addressing the concerns regarding its porous nature. Furthermore, RCA provides a protective shelter for bacteria against high pH environments and mechanical stresses. Bacterial carriers like RCA allow spores to survive for extended periods, contributing to crack healing even when the concrete is cracked at later stages.
Hello, Engineer Charles, are you familiar with geopolymer concrete?
Countries such as Japan, China, India, Germany, and the United Kingdom, among others, are actively researching and adopting geopolymer concrete as an alternative to cement concrete. I am also contributing to the development of geopolymer concrete through ongoing research in this field.
Perfect. Today I am with Rika, who brings with her a solution to address the cracking issue with geopolymer concrete.
The microbial-induced calcium carbonate precipitation, or the MICP technology using urease-producing bacteria, can also be incorporated to geopolymer concrete to provide it with self-healing properties. Moreover, the bacteria can also be utilized to treat the recycled concrete aggregates, or the RCA, to improve their properties.
That's a great idea, Rika. A self-healing geopolymer concrete. Geopo-Hilmer. I can help you in providing an advanced solution to the construction industry, especially with the use of concrete. And with that, let us take part in advancing the United Nations Sustainable Development Goals.
By promoting sustainable industrialization and fostering innovation.
By making cities safer and more resilient.
And by ensuring responsible consumption and production. Beyond innovation, let us also expand our expertise and empower the young generation. Like the American Concrete Institute, we continue to shape the future of construction, driving progress, sustainability, and excellence.
Congratulations, team. An amazing presentation on geopolymer concrete. And with that, we are going to get ready to move to our next and final category. Overall highest score category for this competition. In third place, we have from the Hashmite University. Again, we saw their last presentation, so I won't play their video again, but still like to take the time to congratulate this university on an amazing placement, amazing video. In second place, we have Bangdun Institute of Technology.
That was a building in Beirut in 2026 after a missile attack. It shows a hidden problem that often goes unnoticed. Leaving it unfixed will cost us dearly. In 2023, a single earthquake in Turkey destroyed 160,000 buildings in seconds. In Syria, 8 years of conflict destroyed 900,000. War in Ukraine, disaster in Haiti, and Nepal. Across these 5 major disasters, nearly 2.5 million buildings collapsed. That is roughly 58 million tons of shattered concrete, twisted steel, and broken stone. Most of that rubble is treated as waste, but inside the broken concrete, there's something that we can use as a solution to our climate problem. But how comes destruction is a solution? This is where one idea begins: carbonated, recycled concrete aggregate. To understand why that matters, we need to look back to where concrete starts: the cement kiln. Making cement means heating limestone and clay to 1,450 degrees Celsius. This process, called calcination, cracks limestone apart, releases carbon dioxide, and becomes a clinker. Cement production alone is responsible for 7 to 8% of all global carbon dioxide emissions. That is more than aviation and shipping combined. Now let's go back to the rubble. Instead of borrowing the demolished concrete, we can recover it. When demolished concrete is crushed, sorted through screens, and cleared of steel with magnets, it becomes recycled concrete aggregate, or as known as RCA. The old concrete gets a second life as the gravel inside new concrete. Cleaner and coarse fractions are recycled into new concrete, and the lower quality fractions are used for other concrete-based goods. From those 5 disaster sites, we could recover 21 million tons of usable RCA. That's enough to reconstruct nearly 100,000 new buildings. But RCA has a weakness. Residual mortar stays attached to its surface, making it more porous, more absorbent, and weaker than natural aggregate. The important part is this, that old mortar still contains calcium hydroxide, so the weakness also becomes the reaction site. This is where RCA and carbon capture combined. The carbon dioxide released earlier by the cement can be sent back into the recovered concrete. When carbon dioxide enters moist residual mortar, carbonation happens. Calcium hydroxide reacts with carbon dioxide to form calcium carbonate, or as known as CaCO3, plus water. The calcium carbonate, or limestone, act like a natural filler. They plug up tiny holes and pack the weak spots tightly, making the material much denser. Instead of the gas escaping back into the air, it gets trapped and turned into solid minerals inside the recycled concrete aggregate. This makes the surface stronger, keeps water out, and results in what we call carbonated RCA. So this is not 2 separate ideas, it is one simple loop. Recover the RCA, cure it with carbon dioxide, then reuse it in new concrete. Our innovation takes this natural reaction and engineers it across 3 strategic injection points. Phase 1 is recovery and preparation. Rubble is crushed, cleaned, and graded, so the old mortar on RCA is exposed and ready to react. Phase 2, carbon dioxide curing. In a controlled chamber or curing environment, carbon dioxide diffuses into that mortar and forms calcium carbonate inside the pores. Phase 3 is reuse. The carbonated RCA returns to new concrete with lower porosity and stronger bonding potential. After its service life ends, the cycle can begin again. But does it work? A life cycle assessment study conducted in Singapore shows this process achieves negative 21.42 kilograms of CO2 equivalent per ton of RCA. This is carbon negative concrete. On global scale, this approach could deliver up to 0.64 gigatons of carbon dioxide equivalent reduction per year globally, contributing equivalent to 10 until 35% of the Paris Agreement's negative emission target. This is not a magic fix though. Carbon dioxide curing raises costs by 4 to 14%. Each phase demands precise control of moisture, pressure, and timing, and carbonation lowers pH levels, risking steel corrosion without protective measures. So the goal is not to use the carbon dioxide carelessly. The goal is to use it precisely, where the material design, curing conditions, and durability protection are all engineered together. Most people see waste, we see 21 million tons of aggregate waiting to capture carbon and become something stronger. And the carbon dioxide leaving the kiln does not have to stay a problem. Carbonated RCA brings the 2 storylines together. Rubber provides the material and captured carbon provides the cure. One waste stream helps prepare another. Not all innovations are new. Some are rebuilt from what we leave behind. Thank you.
Thank you and congratulations, Bangden Institute of Technology. Great presentation. And now, in first place for the overall score have University of Philippines, Los Baños. Congratulations on 2 first place finishes. This team has an amazing presentation. We saw their geopolymer for the innovative design category. Thank you to the team for their participation. Thank you for, let's see if we have any representatives today. Congratulations. We will be sending out the results and things at the end of the competition. Feel free to email me if you have any questions. And now, I believe we have with us here today our SciFac chair, Alyssa Naro, who's here today and wanted to give a few words to our teams. Is that okay, Alyssa?
Yeah, sure, of course. Thank you so much. Well, on behalf of SciFac and ACI, we want every participant to know that your ideas, passions, and involvement truly matter to the Institute. Competitions like these, concrete solutions, are opportunities to grow, collaborate, innovate, and become part of the future of the concrete industry. SciFac is very proud to support students, young members, and faculty, and we encourage you to stay involved in ACI and continue contributing to our concrete industry. Thank you for your dedication. Congratulations to all the winners. Congratulations to all the teams. Thank you all the judges, and thank you ACI staff for making this happen. And well, we hope to see many of you in Atlanta. Thank you.
Thank you all. And I didn't want to skip past it. Want to make sure we acknowledge our wonderful judges who helped us out. Thank you all. Some of you are here today, I believe. Without our judges, truthfully, these events would not be possible. They help to curate these events for you all. They help to review all of you guys' information and your submittals. So please, a hand to our judges. Thank you all so much. And thank you to our SciFac chair for that amazing special word for our students. Coming up, we have the ACI Mortar Workability Competition in October. Teams are challenged to create a mortar mixture with the most optimum flowability and stability. The registration is open now. Only the top 40 teams who finish their submission round will be selected to participate in this student competition. So please, 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 we want to urgently tell everyone to get their submissions in so that we can get started with competition and get everything on point. The competition is capped at 40 teams. So only those top 40 who finish the submission round, just to urgently say. Thank you all. The registration round and deadline is September 1st. The final submission will be September 21st. So we want to urgently encourage teams to get their submissions in as soon as possible. Don't wait till the end of the summer. I would hate to have any teams who are missing out on such a great student competition. This is happening in Atlanta at convention. I want to congratulate all of our teams, our advisors, and our competition winners. And we will see you all at the ACI Fall Student Convention, well, that's convention in general, in Atlanta. Thank you all so much for coming. Thank you all. Congratulations to our winners. Thank you all of our advisors. Thank you all of our judges. And have a wonderful afternoon, everyone. If you have any questions, feel free to email me at students@concrete.org. And you can see the results soon. They will be posted to the past winners page. If you have any questions for me or our competition chairs, feel free to send them to me at students@concrete.org. Thank you so much, everyone, for coming.